Greetings, YouTube viewers, and welcome to Santa Cruz's Astronomy on Tap, October 2020 edition. I am Xavier Prochaska, Professor of Astronomy and Astrophysics. I can go by Professor X if you prefer. And I am this week's stand-in host for our wonderful Alexandra Mannings, who is on assignment in the state of Georgia. But I've been thrilled to stand in because this is going to be an outstanding show, and we're absolutely thrilled that you could make it. Most of you, unless you've misclicked altogether, probably know this is Astronomy on Tap and that it's a casual presentation of astronomy to folks like yourselves, often in a bar. Indeed, when we are in a bar, we encourage you to drink out of one of these, one of our Astronomy on Tap glasses, which I'm going to do right now. So I encourage, if you haven't had the opportunity to grab a beer or water or whatever it is that you like to drink, please do so. I am going to be enjoying this one in our Santa Cruz koozie, which you can also purchase from us. Just give us a holler. I'll be drinking from a varietal from San Diego, where I got my PhD, a fine institution known as Pizza Port, who brews their own beer and makes their own pizza, and these days have gone statewide at least. You can buy it at Costco. Help yourself out some of these days. As for the events, I'm going to start us off with some recent news and events. Here first, though, is the order of events for tonight. If you're new to Astronomy on Tap, this is the way we usually run it. I say hello, give us some updates of the news and astronomy. We'll have a presentation. The first will be by Peter Gao. Then a trivia/quiz event will occur. This one will be graded this week, new online, and followed by a presentation from Dr Courtney, which we should all be looking forward to. News and events. This is an image shared by one of my friends on our Slack channel of the smoke covering North America over the last few weeks. That's pretty intense. Without a doubt, climate change is not only affecting the way we breathe and view the sky here in Santa Cruz, it's also affecting astronomy in significant ways. A number of the observatories, both in Arizona and California, are being impacted here just by the smoke. And of course, I think many of you are probably aware of the fires that overtook Mount Hamilton, where our Lick Observatory is located, and threatened quite significantly Mount Wilson down in Pasadena. But they were at least spared direct fire.
X, you're not sharing your screen.
Ah! Thank you. Back to our smoke. I love the dynamics here. The fluid dynamics are pretty intense. You can clearly see the dominant wind patterns, the jet stream, but also some interesting backlash. Other news from the past month, there's this wonderful video, if you will, kind of a video, a set of stills of the images of the black hole, which you've probably seen before, but now they've released a series of individual snapshots from 2009 to 2017 and made a really cool video of it in Nature. Since I couldn't quite grab the GIF off the Nature website, all you get is my kind of four-person attempt at a video. Also pulled from the news, a new book from Brian May, guitarist of Queen, called Cosmic 3D Clouds. I don't quite know what the 3D is all about. There's some kind of 3D rendering, I guess, of Hubble space images. He's the creative director. If that excites you, check it out. And last but not least, measurements of the distance to a magnetar, what we believe is a spinning, very rapidly spinning neutron star with a very intense magnetic field around it. This one, which is in our galaxy, emits some radio radiation in addition to other wave bands. And folks using the VLBI were able to pinpoint its distance from Earth using the technique known as parallax, which now establishes very directly the energetics of this really crazy phenomenon. I'll stop sharing now and bring my face back. With that, I'd like to introduce our first speaker of our first presenter, Peter Gao. Peter, by all means, turn on your video. Let me ask a question or two of you. Hello, sir.
Hello, hello.
This is a virtual welcome to Santa Cruz.
Thank you.
Peter has just arrived in the COVID era. And as we were discussing before we went online, may never actually step foot in a building before he departs for his next position. Nevertheless, we're thrilled to have him here. Peter, maybe where were you previously? Where have you not left as a result of COVID?
Yeah, so I was a postdoctoral scholar at UC Berkeley, where I spent 3 years having fun doing research. And as of September 1st, I'm officially a Santa Cruz postdoc, even though I'm still here near Berkeley. Yeah, not that far away.
No, not at all. A more astronomy related question. What is your favorite telescope and why?
I said no gotcha questions. No, you know, given that I work these days, I work primarily in exoplanet atmospheres, and Jonathan's going to talk about that later. I think good old Hubble is my favorite right now. Some of its instruments have given us some of the best data we've had, and even when it wasn't designed to do that. So tough little ship.
And this one I think is a softball. What attracted you to Venus? Was it the sparkle in the sky? Was it the yellow-brown color? Why Venus?
Why Venus? Yeah, so, you know, Venus has been sort of the neglected stepchild of the solar system. You know, everyone focuses on Mars because it's easy to explore and land on, but Venus is right next door. It's about the same mass, same radius as the Earth. But it's completely different in character and style. So why not take a look and see why it has diverged so dramatically from us? That's why it's very interesting.
Wonderful. I encourage you now to share your screen.
Yeah. All right.
And the floor is yours for this presentation. Thank you.
Right. Thank you so much. Let's see here. Let's do it. And pop that up. And I'm going to assume that it's on, but please let me know if something is off. So again, very excited to be here. My name is Peter Gao. This is actually my first Astronomy on Tap ever, both as presenting and as just being there. I actually never been to one before, even though I've heard all about it. And so I'm very excited today to tell you all about searching for signs of life on Venus and exoplanets. And I'll be starting us off with part 1, life on Venus? Question mark, question mark. And so why all the hubbub about the possibility of life on Venus? Well, perhaps you've seen some of these headlines in the last couple of weeks that seems to say that we might have found potential signs of life in the clouds of Venus. Some of these headlines they're pretty nice. They're nice and descriptive and cautious. Some of them are not so cautious, like aliens were on Venus this whole time, and could there be some sort of sea monkeys on Venus that can dry out and reanimate? Okay, so why all the excitement about life on Venus? What did we actually find? So what we found is a gas called phosphine. So there you go, it's in the headline. And what is phosphine? So phosphine is a gas that's toxic, flammable, and produced by decaying organic matter. So not very attractive, okay? But the very fact that it's produced primarily from decaying organic matter, and as a reminder, decay is the action of microbial life, means that the detection of phosphine, at least on Earth, is indicative of life. And so that's very exciting. Phosphine, in this case, belongs to a whole class of possible gases and possible phenomenon that we call biosignatures. And so what is, in general, a biosignature? And why is phosphine a biosignature, in this case, on Venus? So put simply, a biosignature is a substance or a phenomenon that provides scientific evidence of past or present life. And this is very important, it cannot be generated by non-life. And so you might think, okay, what gases do we have? We have phosphine. What else? What else? But it's actually not the right way to think of it like that. You have to think of both the gas or any substance or phenomenon, and also the context of that substance or phenomenon. what's the background composition of the atmosphere, for example. So to illustrate this, I like to use Earth as an example. So let's assume you're an alien scientist from far away. You can observe Earth. It's very hard to get there. How can you tell that it's teeming with life? So luckily, we don't have to try to brainstorm this, because our good old friend Carl Sagan wrote a paper about this back in 1993, published in Nature, titled "A Search for Life on Earth from the Galileo Spacecraft." And as a reminder, the Galileo spacecraft explored Jupiter for several years. But on its way there, it flew by Earth a couple of times in order to use its gravity to boost it all the way to Jupiter. During one of these flybys, it trained its instruments on Earth and measured its atmospheric composition. And this is what it found. It found a whole lot of oxygen. It found some water vapor. It found some carbon dioxide. And it found some methane. The weird thing about this detection was the methane. And I'll tell you why. So at this point, we have to get into the chemistry concept of equilibrium. A chemical system in equilibrium, and by chemical system, I mean literally any configuration of molecules. It could be the air in this room. It could be some random piece of air out there. It could be whatever is in this bottle that I hope you probably can't see. But whatever it is, it's just a collection of molecules. And a chemical system that is in equilibrium is occupying the lowest energy state. It is by far the most stable configuration it can be. Okay, there's no way for it to evolve into a more stable configuration. Now, disequilibrium, as the name suggests, is any deviation from equilibrium. And that usually takes energy. You have to work. You have to put work in to push a system out of equilibrium. And so I tried very hard to figure out what's the best metaphor to illustrate this concept. It was actually pretty obvious. I have a 2-year-old toddler at home. And what I've noticed is that if we just don't clean the house for a couple of days, we're busy people. Sometimes we don't have time to clean the house. All of his toys will just be everywhere on the floor. And that configuration just stays about the same. The toys can be rearranged on the floor, but they'll always be on the floor, maximally spread out. And so that is equilibrium in our house. The toys cannot get lower than the floor, and so there they stay. Now, in contrast, when all the toys are put back into the toy box, the toy chest, that is disequilibrium, because we actually have to put energy to doing that. And by we, I mean myself and my partner, of course. And just as a system in disequilibrium will tend towards equilibrium, when we turn our backs, well, the toys go right back on the floor. And so hopefully that illustrates what equilibrium and disequilibrium are. Now, in terms of chemistry, in addition to this equilibrium, disequilibrium concept, we also have to understand what happens when you put chemical species that have a lot of hydrogen in them and species that have a lot of oxygen in them together. And so when you do that, they tend to react, forming, among other things, water and other substances. Now, what I show on the left in equilibrium land are two chemical systems that are in equilibrium, but separated from each other. So on the top, there's the hydrogen-dominated species, such as a mixture of hydrogen gas, methane gas, and phosphine gas. And they are in equilibrium because the hydrogen just likes to stay around itself. Now on the bottom, you have oxygen-dominated species like water, oxygen gas, and CO2. And they're fine, just hang out on their own. Now, if you take a little bit of the oxygen species and put it into the H species bucket, or vice versa, as you do, as you see on the right, then terrible things happen. In this case, you have fewer hydrogen-dominated species, and they're going to be gobbled up, and you're going to end up making a lot of water, also some CO2 from the carbon in the methane, also some phosphates, which are phosphorus bonded to oxygens from the phosphine. But we don't see that on Earth, right? We see both oxygen species and hydrogen species like methane. And so Earth is wildly out of equilibrium. And the only way for that to happen is for some process to generate methane and phosphine in such a high rate that it can keep the system out of equilibrium. And based on our understanding of geochemistry and geological processes, no such processes can do it. They're very, very slow. And the only thing we can think of right now is life. And so life can produce methane fairly quickly, and quickly enough such that it can push Earth so far out of equilibrium. And so that's why you would say, methane could be a biosignature, but more importantly, the context of methane in an oxygen-dominated atmosphere is very much a biosignature. But, being free of specific gases, chemical disequilibrium in general is a biosignature, provided that the disequilibrium cannot be explained by non-biological processes. Okay, so let's go back to Venus. First of all, a little overview of Venus. It's not a very nice place to live. So here I show how the temperature in the atmosphere of Venus changes as a function of height in the atmosphere, altitude. At the surface of Venus, which, by the way, this background picture is the surface of Venus from one of the landers, almost in real color, I believe. Now, the surface temperature is 733 Kelvin, which is about 860 degrees Fahrenheit. So that's very, very hot. So unless you're someone like this and think this is all great, it's balmy, and get a tan, there's not going to be any life there that we know of. But luckily, the temperature drops as you move up in the atmosphere, such that at around 50 and 60 kilometers altitude, it's nice. It's like room temperature, actually. There's also the matter of a bunch of sulfuric acid cloud droplets, just a minor detail. Now, why am I talking about these? Well, phosphine, right? Phosphine was detected in Venus' atmosphere, was found in the cloud layers right around the temperature where it is fine for life as we know it. And phosphine, being a hydrogen-dominated gas, persisting at a relatively high abundance in a carbon dioxide-dominated atmosphere, is pretty excellent example of chemical disequilibrium. And so this is the reason for all those headlines. So the discovery was phosphine, and the interpretation was that no known chemical geological processes can explain the abundances. But is that actually true? So here's the issue. There's a lot we don't know about Venus. So this, being another planet that has not been explored nearly as much as, say, Mars, there's actually quite a few unknowns about the atmosphere, surface, and interior of Venus. For example, could phosphine be generated by some unknown gas or solution chemistry in the cloud droplets themselves? Now, I said they were sulfuric acid, but they're actually a mixture of sulfuric acid and water, and probably some phosphorus and chlorine species as well. And when you pelt these droplets with UV radiation from the sun, can something happen that can create phosphine? We don't know. This has not really been measured in the laboratory. What about the composition of the atmosphere below the clouds? Well, we've only had a couple of measurements at very specific points in the atmosphere based on landers. And so we don't actually know for sure what's down there. Could some unknown chemical reactions be causing phosphine production? What is the surface of Venus like? Sure, we have pictures, and we seem to have some measurements that it's maybe similar to lava that pours out of the Hawaiian volcanoes, basalt. But what's the actual elemental abundance? And finally, what is the interior of Venus like? We don't know. What's actually coming out of volcanoes on Venus? Could they be actually blowing off phosphine? We don't actually know. And finally, could it be life? We don't know that. And so I guess the point here is that there's a lot we don't know about the Venus atmosphere. And so whatever is generating the phosphine, it could be a lot of things. Now, whether it is life or not, the most important thing is that it's raised interest in Venus. And so here is a tweet from Jim Bredenstein, the NASA administrator. He said a bunch of stuff, and then at the end, it's time to prioritize Venus. So that's very important. I smashed that like button. I retweeted the hell of it. But the point is, we might finally be able to focus on exploring essentially our evil twin right next door. Now, luckily, there are Venus missions in development. There are actually several across the world. I'm just going to highlight two here from NASA, the Da Vinci Plus mission and the Veritas mission. They're both acronyms. I actually don't know what they are off the top of my head. The V is probably Venus. It's probably a good guess. They're very different missions, though. Da Vinci Plus is a probe that's going to fall through the atmosphere of Venus, collect some samples, and beam it back. No, sorry, beam the measurements back, not the actual samples back. That'd be great. Veritas is going to be an orbiter that will map the surface of Venus at very high detail, and so we'll know if there's any active volcanoes going on, and also the composition of the Venus to some degree. Both of these have not been selected, have not been approved to go forward, but they are currently competing to go forward. And my opinion is, why not both? That'd be awesome. Okay, so this is my last slide. I'd just like to end on a thought about how certain we should be of discoveries when we don't quite understand what's happening in these atmospheres. Now with Venus, like I said, there's a lot of unknowns, but we have the luxury of sending probes there, and maybe even one day sending people there, at least to hang out in the cloud decks. With exoplanets, which Jonathan's going to talk about next, it's going to be very hard to go there and get some ground truth, so to speak. And so what's going to happen one day when we may detect disequilibrium in these atmospheres? How confident will we be to say that that is caused by life? And so, that's a question that keeps me up at night as both a Venus scientist and an exoplanet scientist. And maybe we'll do the same to you now. So with that, I'll stop and I'll thank you, and I'll answer any questions and take any comments. Thank you.
Thanks, Peter. That was fantastic.
Thank you.
Folks, you're encouraged to type in questions on the YouTube channel or other social media opportunities while you're taking that opportunity. Let me begin with a question. Why phosphine? Why did your team, did you start there? Was it, and what other biosignatures did you hypothesize, or have you tried over the decades of studying Venus?
Yeah, so given the here, I guess I can stop sharing for now, unless someone wants to see slides again. So I should mention that the team that discovered phosphine, I actually wasn't on that team, although I'm connected to some people on that team. That initial study was actually just to look for trace gases on Venus, and they were trying to essentially stress test these telescopes and see, well, there's no way phosphine can be in this atmosphere. There's so much oxygen in it. There's no way we're going to see anything. But then they saw it, and so it was very much an accidental discovery. And before that, the idea of life on Venus, after we figured out that the clouds were sulfuric acid, it was under a runaway greenhouse state. There wasn't really much thought of possibility of life, although the idea of life kind of around the cloud droplets have been around in the background for a while.
A related question from the great internet, from Jessica: why have we not detected phosphine on Venus previously?
Great question. Well, I guess one thing, there's a couple of ways to answer this. One thing is that nobody thought to look for it. Again, it's just such a wacky gas to have in Venus's atmosphere. And so even though it could be there, people just might miss it. It's also about the capabilities of the spacecrafts, right? So this specific measurement of phosphine took place in a very long wavelength. So this was stuff that you could have basically only done on Earth with some of these radio telescopes, or you built special radiometer that you would send to Venus. The spacecraft that were there before mostly did measurements of infrared light, and there are some phosphine features, but they're drowned out by the CO2 in the atmosphere. There was a paper that actually just came out. There was an article that just came out that's going to be peer reviewed, I believe, where they looked at old data from probes that went in through the atmosphere that collected samples, and based on the masses of the molecules that were collected, some of them may actually be phosphine, but it's very hard to interpret that. It's very degenerate. Like, it could also be something else, and so I would say actually continue looking at those archival data, because it might actually be in there now that we know that it actually could be there. Yeah.
A question from Joe: is Bridenstine's evil twin named Frankengroom?
Yes, yes. Yeah, I have a NASA T-shirt, so I know all the secrets, and the answer is yes.
A question from Dina: how confident are we that the phosphine was actually detected at the levels reported?
I love this question. Okay, yes. So I won't go into the gritty details, but there is a lot of steps going from just collecting the data and actually plotting it up and showing there's, a peak or a drop due to phosphine absorption in the atmosphere. How much do we trust it? I'm not a radio astronomer myself. Talking to some radio astronomers, there's sort of a wide range of opinions. Some say that because, oh, by the way, this is a detail I forgot to mention, they actually detected it using 2 telescopes, completely separate. James Clerk Maxwell telescope on Mauna Kea and the ALMA telescope in Chile. So 2 completely different radio telescopes, both found the signal, though one of the telescopes, the signal was a lot noisier than the other one, I would say that. So that's very good. So that's a good test. They also did, when they were converting the data from sort of the raw data to what you actually get, they did some interesting tricks that sometimes it's necessary to do with radio astronomy. Other times it might introduce spurious signals. But I think the effort now is for other groups to work with the same data and see if they get the same signal. I think the efforts are already starting there. And so we'll know within a couple of months what the results are from other groups. Yeah, jury's still out.
Last one for you, sir. What other processes might generate phosphine under the sorts of conditions expected there?
Yes, that's a great question. So there are actually lots and lots of processes that could generate phosphine. The key is to generate it at the abundances that was detected. So the actual abundance actually is not that much at all. It's 20 parts per billion. So for every billion CO2 carbon dioxide molecules that are in this atmosphere, there's 20 phosphine molecules. That doesn't seem like a lot, but if you assume equilibrium in this atmosphere, it's like less than 1 molecule. And so what are these other processes? Well, they are reactions from phosphorus compounds that is actually like one of the phosphorus salts, which is like 4 phosphorus bonded with 6 oxygen, or 4 phosphorus with 10 oxygen. And that you expect in Venus atmosphere because there's a lot of oxygen. And there are reactions that you can get from there through reactions of sulfuric acid or water that can give you phosphine. But the reaction rate appears to be extremely, extremely slow. So you wouldn't get nearly as much phosphine as was reported in the paper. And so I think that's why they were like, well, either it's something we know nothing about, some process we don't know about, or maybe it could be biology, which kind of opens the door to a lot of interesting possibilities. Yeah.
Fantastic. Well, we will be staying tuned, and those of us in the department will be continuing to have you give us updates on this fantastic story. Thanks so much for joining us. You did wonderfully in your first AOT. I hope you come back someday.
I'll do that. That sounds great. Yeah, thank you. Thank you so much.
Great. So we're going to now do our trivia/quiz. I'm going to share my screen and show the slide. In the YouTube chat window should be the form, if you wish to play along at home, the form that you can fill out to answer the questions, be graded, and be announced as our trivia winner at the end of the program, if you, of course, beat out everyone else. We'll begin. This is the October Trivia. Compliments of Erica Gonzalez. Do a fantastic job. The first topic is seasonal astronomy. We'll warm you up with a bit of seasons. Because I am still in love with you on this blank moon, Neil Young sang a beautiful tribute to the full moon you are seeing tonight. Fill in the blank. Neil Young sang a beautiful tune tribute to the full moon, which went like, because I am still in love with you on this blank moon. This one is a multiple choice. Again, if you've got access to the internet and wish to play along, you can fill out the Google form and be graded. Question 2. We will see another full moon this month on October 31st, Halloween. Spooky indeed. What is the special second full moon referred to as? That's an open answer for you. And Erica gave you a nice little hint if you're unawares of this name for two moons in the same, two full moons in the same month. We move on to astronomical news. Our beautiful sister planet Venus has made headlines of late. What gas was found in its atmosphere that have generated those headlines? If you were paying attention to Peter, I think you'll be on top of this one. What gas was found in the atmosphere of Venus this month, as reported by our scientists that have gotten great excitement about the notion of life? Number 4, still hope you were paying attention. Which layer was it found in? Which layer of the atmosphere of Venus was this gas, which I won't name, found in? Multiple choice: A, topmost; B, middle; C, near the surface; D, ejected gas. Question 5. According to the highly reputable bad news source at notscience.com.org, NASA confirmed the detected toxic gas was due to what? What, according to this wonderful news source, did NASA confirm the detected toxic gas was due to? Open in. Number 6. Okay. Though organic life forms can produce the toxic gas, scientists are looking into other geological processes. Which of the following processes is being explored? A, volcano; B, Venus quakes; C, Mercury in retrograde; or D, magnetic activity? Which of the following processes are being explored as alternative explanations for a life interpretation? A few more on topic. Set to launch in 2021. How will JWST, the James Webb Space Telescope, be used by exoplaneteers? Will they A, study exoplanet atmospheres; B, study exoplanet surfaces; C, spy on aliens; or D, discover exoplanets in other galaxies? What will these exoplaneteers be using JWST to discover? Number 8, biomarkers are chemical signatures in the atmospheres of planets that may house life. Which of the following is not a biomarker? A, methane; B, dihydrogen monoxide; C, ozone; or D, diode? Which of those listed there, methane, dihydrogen monoxide, ozone, or diozone, which of those is not a biomarker? Number 9, which was the first confirmed terrestrial exoplanet? Which, into the day, was discovered by our very own Professor Natalie Battaglia? Was it A, 51 Pegasi b? Was it Kepler 10b, Kepler 186f, or the Earth? The first confirmed terrestrial exoplanets. Which of those items is the proper name of that planet? And that is it for the trivia questions. We will return for the answers at the end of the show. But we will now move on to introduce our next speaker, our second presenter, Jonathan Fortney, Professor Jonathan Fortney of our Astronomy Department. Paging Dr. Courtney. Come on down. We see you, we now hear you. Thanks for coming back to Astronomy on Tap. Always a pleasure to have you here. I think
Great
you
to
may
be
be our
here.
first two-timer, maybe not. You're certainly one of them. While we've been here before, I still have a few questions by way of introduction to the audience. Let me begin by congratulating you on the 2020 Farinella Prize.
Thanks a lot.
What is it? What is this prize, and how did they present it to you?
The Farinella Prize is a prize given out every year for important work done in studying planets. And it's given out by the European Planetary Science Congress, and they've been giving out every year for the past 10 years. And normally I would have gone to the conference in Europe to receive the award, but this time I gave a talk remotely on Zoom. And I think they're going to mail my certificate to me in the mail someday.
Congratulations.
Thanks.
I know, of course, that you're no stranger to the solar system. What's your impressions of these new observations of Venus?
I think it's quite intriguing. I'm very interested in what other radio astronomers think of the original detection. I think we're going to be seeing a lot of reanalysis of that data set over the next few weeks, probably.
Good. And sticking with that topic, sort of, what next generation solar system mission has you the most excited?
I think the Dragonfly mission to Titan, which is a really big moon of Saturn that has an atmosphere thicker than Earth's. It's a quadcopter that's going to fly around in the atmosphere of Titan in the 2030s. To me, that's probably the coolest thing we'll have in the solar system for a long time.
Well, great. Well, welcome back. The floor is now yours. Please share your screen, and I will come back at the end of your presentation.
Okay, I think we're there. So I'll be talking tonight about planets around other stars, which are called exoplanets, and the prospects for searching for life on these planets. It's a great complement to Peter's talk. In the solar system, we can study our neighboring planets in a lot of detail. But if life is a rare phenomenon, we're going to want to search for a lot of different planets for life. And planets around other stars are a huge sample size. So we can talk about how we might go about trying to find life on these planets as well. And that's what I'll be talking about for the next 15 minutes or so. So I think we all know that planets come in different sizes. We have gas giant planets like Jupiter and Saturn. Jupiter is about 300 times the mass of the Earth. We can see down at the bottom small planets like Earth and Venus, Mars and Mercury. So planets come in different sizes. But all these sizes are small. So to scale, we have the sun in the middle. We have Jupiter down there, and you can just make out the Earth. The sun is 1,000,000 times larger than the Earth. And so all planets are small compared to stars typically. And that can make them hard to find and hard to see. Another reason why is that stars are bright, planets are not. A planet like the Earth is about 10 billion times dimmer than the sun. So if we want to find planets like the Earth around other stars, we have to be able to see planets that are about 10 billion times dimmer than their parent star. On the right is a real image of a planet that's 1,000,000 times dimmer than its star. The star is blocked out via very nice technology that allows us to see the faint planet nearby it. So that's a big Jupiter-like planet that's 1,000,000 times fainter than its star. So taking a picture of an Earth-sized planet is going to be quite hard. It's beyond our technological limits today. However, astronomers are pretty clever, and they've devised ways to find planets that use the fact that stars are bright to our advantage rather than our disadvantage. And I'll talk about that for the next 5 minutes or so. So this method of using the star's light, one of them is called a transit. And in a transit, if we see another planetary system edge on, we might be able to see a planet pass directly in front of its parent star if we're looking at a distant star. A planet the size of Jupiter would block out about 1% of a sun-like star's light. A much smaller planet like the Earth would block out about 100 times less, about 0.01% of its star's light. So this transit could happen over and over again once per orbit. If you're in a 100-day orbit, that dimming should happen every 100 days. If you're in a 10-day orbit, that dimming should happen every 10 days. So we can figure out the orbit of planets this way. It turns out this is a pretty good way to find exoplanets. And it turns out in our own solar system, we can see transits sometimes. So as seen from Earth, we can occasionally see Mercury and Venus pass directly in front of the sun. That's a transit. Our orbits are a little bit misaligned, so we don't see it all that often. This is one of my favorite images. This is a 2004 transit of Venus. We can see the sun rising off the Florida coast. Venus, pelicans, and fishermen. Now, transits don't happen very often. There was one in 2004 for Venus. There was a Venus transit in 2012. The next one is going to be in year 2117. So if you want to see the next Venus transit, get your exercise, eat your vitamins, work out. It's going to be a while. But transits are important for a lot of reasons. One of the most important is that a transit can allow us to see something about a planet's atmosphere. This is a zoom in from a small space telescope that always points at the sun. This is an image of Venus passing in front of the sun, and we can see a thin crescent around the edge of Venus. That's actually due to Venus's atmosphere. It turns out this thin crescent was seen about 250 years ago by a Russian astronomer named Lomonosov. And that was how we discovered that Venus had an atmosphere. This incredibly thin crescent was seen. So this suggests that we might be able to learn something about exoplanet atmospheres by looking at transiting exoplanets, because we did learn something about Venus's atmosphere from a transit. So let's try to find transiting exoplanets. And this has been done over the past decade. This is a picture on the lower left of the Kepler mission. NASA's Kepler mission stared in one patch of the sky near the constellation Cygnus. And Kepler was a specialized space telescope. It was like a big 100 megapixel space camera built to do one thing and do it really well. And that was to look at the brightness changes of these little dips of the parent star's light. And what Kepler showed us for the first time is that planets are very common. And Kepler itself found about 4,000 exoplanets. And we were able to assess how common planets are in our galaxy by looking at this patch of light, this patch of sky in the Milky Way. This is one of, I only have two graphs, I think. So this is one graph I just wanted to show. On the left here, we have the size of planets, the radius of a planet compared to Earth. So we have one Earth radius, and we have Neptune size, and we have Jupiter size. And this is the period in days, 10 days, 100 days. So Earth is one Earth radius, and it's in an orbit of around 365 days. Kepler found 4,000 planets. All these yellow dots are planets that Kepler found. It found big planets, smaller planets, tons of planets that are around the same size as the Earth, rocky planets. But because of reasons of how Kepler was designed, it only found planets close to its parent star. There's definitely tons of planets further away from the star, but Kepler wasn't able to see them. So you might think, well, the planets that Kepler found are probably way too hot to have life on them if they're so close to their parent star. But that might not be true. So astronomers have this idea of a concept called the habitable zone. And the habitable zone is how far away from your star the planet needs to be to potentially have water, liquid water on the surface. A planet like Venus is too hot. It can't have liquid water on its surface today. Planets very far from the star, like beyond Mars, are too cold to have liquid water at the surface. But Earth is in this Goldilocks zone where it's not too hot, not too cold, it's just right. So if we find planets in the habitable zone that are around the same size as Earth, those are planets that potentially could have surface water. They could have surface life, and surface life is important because surface life can change an atmosphere's composition. And that's one of the things that Peter talked about, these biomarkers, where we're trying to look at changes to an atmosphere's composition to different gases that are due to life. And so it turns out that these close-in planets may not be bad spots to look for life, because it turns out there's a wide range of stars. Some stars are really big and hot. Some stars are very small and faint. The sun is called a G star. It's kind of in the middle, more or less. These big stars are really rare. These small stars are a lot more common. And so if you think about the Goldilocks zone, the habitable zone, we can kind of ask, well, how big is your campfire? If you're around a hot blue star, you want to be further away from that campfire. You want to be, your habitable zone is further out. If you're around a small faint star, you want to be close into that campfire to stay warm. The habitable zone is going to be closer in, and the sun's more or less in the middle. So if we can find a lot of these cooler stars, then their habitable zones are close in. So if we find close in planets, they might not be too hot. They might be just right. And it turns out that if you look around us, if you look around all the stars within 30 light years of the sun, it turns out there's none of these big O stars, none of these big B stars. These faint red campfire stars, the faint campfires, the M stars, are the majority of those stars. About 75% of all stars are these faint stars. So if we can find planets around these nearby faint M stars that are really red, those might be good places to find life if we can find close-in orbits around them, because transits tend to find close-in planets. And there's another space mission going on now called TESS. My pointer might be frozen. Okay, it started. So the TESS mission is surveying the sky. It's looking for these faint red stars, and it's finding transiting planets around them. It's looking in the celestial southern hemisphere, then the celestial northern hemisphere, in all these patches of the galaxy. It's surveying everywhere near us, in every direction, trying to find transiting planets around these small, faint red stars. And these are planets we could potentially follow up to learn something about their atmospheres. Again, just to repeat, TESS is finding planets around these nearby faint red stars. And so we can probe these planets around these faint red stars, these cool campfire planets, very soon, like really soon. And how can we do that? To learn about their atmospheres. That's with the James Webb Space Telescope. So the James Webb Space Telescope, or JWST, that's going to be launching next summer in about a year. And we're going to use that to look for atmospheric molecules, for biomarkers in a small number of planets to learn about the composition of those planetary atmospheres. This is James Webb being assembled at NASA Goddard. It's now fully assembled. They're doing final tests, and it's expected to be launched next year. You can see, compared to a human, it's pretty big. It's about 20 feet across, whereas Hubble's about 8 feet across. And so the idea is that when the planet passes in front of its parent star, if you're looking from Earth or you're looking from James Webb towards this exoplanet, we're looking for gases in the atmosphere of the planet. And these gases are going to have their fingerprints. Different molecules absorb light differently. Oxygen absorbs light differently than methane. So if we look at these fingerprints of these molecules, we can determine if these molecules are in the atmospheres of these planets. We can try to find things like methane, ozone, water vapor, carbon dioxide, these same things we see in our own atmosphere. So that's going to be happening literally starting in 1 or 2 years, which is incredibly exciting. But we're already thinking about what we want to do next. It turns out the sample of really good targets for James Webb for these nearby systems is probably very small. Although James Webb will probably get spectra of 100 or 200 planets' atmospheres, maybe less than 5 are going to be suitable, are going to be habitable zone planets around these small faint stars. So the targets, there's just not a lot of them. We also think that these close-in planets may lose their atmospheres relatively easily because these small faint stars pump out a lot of X-rays and ultraviolet light. So one of the things we'd like to know from James Webb is, do these planets even have atmospheres? So the next part of my talk is really, what can we do to search for potentially Earth-like planets around stars like the sun, something that might really be a lot like Earth. And so then this comes back to direct imaging, trying to take pictures rather than transits. This is the state of the art over the past decade. These are 4 big Jupiter-like planets in orbit around a parent star. The parent star has been smeared out due to really fancy technology. And we can see over the course of 7 years, from 2009 to 2016, these 4 planets orbiting around the star. We can take pictures of these 4 planets. We can also take a spectrum to see what molecules are in these 4 planets' atmospheres. We'd like to do the same thing for more Earth-like planets. These planets are all about 1 million times fainter than their star. So what we need to do is go 10,000 times fainter to planets 10 billion times fainter than their star. This is a computer simulation of a space telescope that would be able to do that. It's a picture of Jupiter, Venus, and the Earth. The sun, the imaginary sun has been blocked out, even though it's 10,000 times brighter than the Earth. And this is a picture we hope to achieve if we were looking back at our own planetary system. This is something that we hope to be able to do in about 25 years, and I'll talk about that. So what Earth looks like, in addition to taking a picture of the Earth, you'd like to know what molecules are in Earth's atmosphere. And it turns out we of course know what Earth looks like. This is Earth's reflectivity at different wavelengths, so that the colors of light we see are here from blue to red. If you go to the infrared, you can see a bunch more molecules, things like ozone, oxygen, water vapor, methane, carbon dioxide. These are the biomarkers that Peter talked about. We'd like to be able to see these in other planets as well. Across colors of light, more than we can see going into the infrared. You can simulate what this might look like to a fancy space telescope. And this is the simulation. This is, again, the brightness versus wavelength. Again, this is the part we can see. Earth looks blue because we have a lot of Rayleigh scattering. So Earth looks blue. It's bright at blue wavelengths. And as you go to longer wavelengths, Earth, you would be able to see these molecules: water vapor, oxygen, carbon monoxide, methane. These are the fingerprints of the molecules we'd like to see. And so there's NASA studies today to figure out what sorts of telescopes we'd like to have in space in the future. It turns out if you want to go 10,000 times dimmer, you cannot do that from the ground. You have to build a space telescope because Earth's atmosphere blurs everything out. And so the idea would be to build a space telescope that's either twice as big as James Webb and uses technology to black out the star's light inside the telescope. Or you might be able to build a telescope smaller than James Webb, but you fly a separate spacecraft that blocks out the star's light. This would have to unfurl in space, and that would block out the star's light. This blocking out the star's light is the most important thing. It's really like trying to see a firefly, that's the planet, around the spotlight, that's the star, but from a distance of maybe 3,000 miles from Santa Cruz to New York City. So the planets are super faint and super close to something much brighter. So it takes really big advances in technology to be able to do that, because we have to do that so much better than we can do it today. So the best idea we have so far, folks working at NASA, folks working at universities like UC Santa Cruz, is something called Luvoir, the Large Ultraviolet Optical Infrared Telescope. This is a space mission concept where you'd build a telescope and launch it into orbit that's about twice the size of James Webb. And you could optimize it to block out the star's light. And you might be able to take spectra of about 40 to 100 potentially Earth-like planets around sun-like stars. So to really look at things that have the same temperature as Earth around stars like the sun, to see if the planets are like the Earth or not. So this is really trying to observe another pale blue dot. People talk about the Earth as being a pale blue dot in space. And so one of humankind's most sought after goals for such a long time is to understand our place in the universe. And that really is within reach. We are the generation that can make plans to think about how we might do that. Both 1 or 2 years from now with the James Webb Space Telescope for a small number of planets, and then in the 2040s with a much larger, more capable telescope optimized to looking for planets like the Earth. So the takeaway points, these are my last 2 slides. Exoplanets provide us with a sample of many planets, and a lot of them are certainly very unlike our own. Within 2 years, we can begin to assess whether some Earth-sized transiting exoplanets have any similarities to the Earth with the James Webb Space Telescope. And in the 2040s, we can start to look for planets that potentially might be like the Earth around stars like our own sun. And we can assess how common signs of life are in our nearby region of the galaxy. We can do that in our own lifetimes. I just want to mention at the end that at UC Santa Cruz, we have a new astrobiology initiative started by Professor Natalie Batalla. And we have a lot of people working in astronomy, Earth and planetary sciences, physics, biology, chemistry, biochemistry, trying to understand how life originated on Earth and how we can try to find signs of life on other planets. So thanks a lot. I'm happy to take any questions.
Thank you, Jonathan. That was fantastic. While people are typing them in, and I am receiving them, let me start you off with one related to James Webb. If things go extremely well and the stars align, in 2 years, what is the data set that makes the headlines? The one that you're just dying to see.
Yeah, there's a really crazy planetary system called TRAPPIST-1. TRAPPIST-1 is around a very faint, very small star. The star is 1,000 times fainter than the sun. And it has 7 planets all about the same size as Earth, really close in, really packed in close. It has 7 planets about the same size as the Earth. I think it's 4 of them are hotter than the Earth and 3 of them are cooler than the Earth. But that is going to be the premier system for taking spectra of the atmospheres of those planets to assess whether or not maybe 1 or 2 of them are somewhat similar to the Earth. So that's the first data set that I think a lot of people are going to be interested in. People will start making observations in 1 or 2 years, but it's going to take a few years to actually build up a high enough signal to say much about those atmospheres, though.
First question from the great internet. How hard is it to disentangle the spectra to see the signatures of each of the molecules or biosignatures in a planet's atmosphere?
How hard is it to disentangle? Yeah, it depends. There's some wavelengths of light, there's some colors of light where 2 molecules absorb at the very same wavelength, and that can be problematic. That was something that was actually difficult for the Venus observations. There's another molecule that absorbs at a very similar wavelength to phosphine, at least where that phosphine was detected. At other wavelengths of light, the molecules don't overlap. So usually the confusion isn't from multiple molecules absorbing at the same wavelength. Sometimes the confusion is really sort of disentangling what's happening in the planet's atmosphere compared to what's happening in the star's atmosphere.
Gotcha. Speaking of phosphine, have we discovered phosphine in some other exoplanet or perhaps any other body beyond Venus?
Yeah, that's a great question. It turns out phosphine is fairly easy to see in Jupiter and Saturn. The reason why it's not so remarkable there is phosphine is PH3, phosphorus, and then 3 hydrogen molecules. And Jupiter and Saturn have tons and tons of hydrogen. So phosphine is the natural states of phosphorus in parts of Jupiter's atmosphere and Saturn. So phosphine has been seen in those atmospheres for a long time. And in Jupiter-like exoplanets, we might be able to see phosphine as well, but it wouldn't be that remarkable. It would help us learn about the chemistry of those planets. I'm not aware of phosphine being seen anywhere else, but I could be wrong.
The concept of the separate shield, the second concept you described, how far out would that shield need to be?
Yeah,
and how hard would it be to align it to the precision required to see
so that's called a star shade. That's
star shade.
Star shade is the thing that unfurls with the petals. That's being worked on at NASA JPL, Jet Propulsion Laboratory in Pasadena. Gosh, I'm forgetting off the top of my head. I think it has, the size of the craft would be, I think like a couple, like a few hundred feet, pretty big, several hundred feet, maybe 200 feet. And I think it would have to be lined up, I want to say 1,000 kilometers in front of the spacecraft, something like 1,000 or 10,000 kilometers. And so you would need a very precise alignment. So you can't see my hands, very precise alignments. But there's been work on other NASA and European space telescopes to work on that precision alignment by bouncing lasers off of each other. And so that is thought to be a solvable problem.
Another question, I'm still parsing myself. What about certain moons of further out exoplanets that could be warmed by the planet's gravitational pull?
Yeah, so I think, so like a moon like Io around Jupiter is very far from the sun, but it's actually very warm. And that's because of tides. It has tidal heating due to its orbit around Jupiter. And so it's true that you could imagine moons that are outside of what you would call the habitable zone, that could be warmed due to their orbit around their giant planet. And so we think like Europa, which is just outside of Io's orbit, that has liquid water beneath its thick icy crust. So that could happen. The trouble with something like that is that we don't know if that sort of subsurface life could actually affect the atmosphere. Europa doesn't even have an atmosphere. And so being astronomers, looking at other planetary systems, we really need to think about things that could affect the atmosphere, because that's the part we could see. But that's a really good point, that the habitable zone, Goldilocks zone concept is, we know it's too simple, but it's just probably the first place to start.
Well, that's probably a good spot to stop then. Jonathan, thank you so much for coming back.
You're welcome. Great to be here.
That was really enlightening. We will finish with a review of the quiz and an announcement of the winner. Let me share my screen again. Oops. And review the answers. Here they are rather quickly. The fill in the blank answer was harvest. I am still in love with you on this harvest moon, as sung by Neil Young. I suspect everyone caught number 2. The blue moon, having 2 full moons in the same month, is known as a blue moon. I hope that everyone that stayed through the end learned about phosphine today. It was certainly new to me just a few weeks ago, but I don't think I'll ever forget it. The layer of sulfur where phosphine was discovered on Venus is at the middle. I believe, if I remember correctly, it was about 60 kilometers above the surface of Venus. The bad news source in notscience.com.org reports that aliens were the source of said phosphine on Venus. One of the processes that is being explored to explain phosphine that is not biological would be volcanoes on Venus. As Jonathan just explained, James Webb Space Telescope will be used to just study the exoplanet atmospheres. And I already forgot the name of the system that is going to be most of the 7 planets that's going to be most sought after in the first couple of years. Stay tuned for that. As he showed in his spectra, if you were paying attention, methane, ozone, dihydrogen monoxide are all biomarkers, which leaves diozone as the out. Kepler 10b is the first confirmed terrestrial exoplanet. And that was our quiz. We had 3 runners up for second place with 7 correct answers. They were Jessica Johnson, Kuzbu, and Dina. Congratulations for second place. Well done. This was a hard quiz, 7 out of 9. I did not achieve myself. And in first place with a total of 8 out of the 9 possible correct answers was Heidi Simpson. Congratulations, Heidi. Thanks for playing. And as I come back live for the last minute here, thanks everyone for attending. We will return on the first Thursday of November. I believe it's maybe the 5th, 6th, something like that. And our presenters that month will be our own PhD student, Sunil Simha, and his colleague, Jay Chitty, who's a graduate student at the University of Colorado Boulder. And they will educate you, if you come to watch, on the phenomenon known as fast radio bursts. And I am fully expecting to be replaced by our very fine host, Alexander Mannings, who will have returned from Georgia. Thanks, everyone, and have a great rest of your night.